Welcome back to the deep dive. If you are here to gain knowledge quickly but, thoroughly, you are definitely in the right place. We take your source material articles, research, your notes, and we distill it all into instant expertise.
And today's topic is a big one.
It really is. Today, we are undertaking a critical deep dive into something that is, fundamentally restructuring the world of intelligent systems. We're talking about agentic AI.
It's such an essential topic right now. We're well past the hype cycle for just large language models. Now we're talking about autonomous AI,
Right.
systems that don't just generate text or follow a script, but actually have the architectural capacity to perceive, reason, act, and learn all on their own.
So our mission today is to synthesize that architecture, the mechanics, the security needs, and of course the scaling requirements for these systems.
Exactly.
We need to understand not just the buzzword, but what actually makes them function as autonomous entities in the real world.
That's right. We're going to focus on the foundational principles, which, it has to start with defining the architectural shift itself. This isn't just a new feature set.
It's a whole new paradigm.
It's a new paradigm.
Okay, let's unpack this. So if we're defining agentic AI, our sources were crystal clear. It's built on 4 core interdependent pillars.
Absolutely. When we define agentic AI, we are talking about systems built specifically around perception,
Okay.
reasoning, action, and learning. And these aren't just, sequential steps. They form the entire operational architecture.
The agentic mindset.
The agentic mindset, exactly. That's what allows the AI to function with autonomy.
That sounds like we're giving the AI system a brain and limbs to actually execute its decisions. But if it relies on an LLM underneath, what's the crucial difference? How is this different from the traditional AI we've been using for years?
The key is that traditional AI is fundamentally static, whereas agentic AI is dynamic. Traditional systems, they rely on predefined rules, decision trees, or static data sets they were trained on. If the world changes, that system, it breaks, or it needs costly manual retraining.
So like a traditional fraud detection model sees a type of transaction it was never trained on,
Yeah.
and it just defaults to a known rule, or it fails.
It fails. It's highly talented, but it's strictly scripted.
Right.
Precisely. Agentic AI, by contrast, is designed to constantly interact with a live environment. It has to reason through new real-time problems, and, this is the most important part, it must learn from the outcomes of its actions.
A feedback loop.
That capacity for continuous self-guided improvement is the central element separating the two. It makes the agent perfect for complex, unstructured, and unpredictable tasks, which minimizes the need for constant human intervention.
Okay, but the moment you introduce that continuous learning and that environmental interaction, you introduce complexity,
A lot of it.
which implies that not all agents are created equal, right, in
Right.
terms of their intelligence or what they're supposed to do.
That's a fascinating point, and it leads us directly to how we categorize these agents based on their operational scope. We really see 3 key categories that often work together.
Let's start with the simplest one. This is probably the backbone of any high-speed operation.
That would be the reactive agents. They operate on simple stimulus response loops. They don't have complex internal models of the world or plan for the future.
So if X happens, do Y.
Exactly. If a data stream exceeds a certain threshold, the reactive agent fires off a notification. They're fast, reliable. Think of them like microservices for handling critical, immediate inputs.
Then you move up a level in complexity to agents that actually start looking ahead.
Those are your proactive agents. They maintain an internal model of their environment and can anticipate future needs or changes. They don't wait for you to tell them what to do.
So they're not waiting for the trigger.
No, they might kick off a process based on a time-based forecast or predict potential system failures and start mitigation steps before the failure even happens.
And finally, the type that's driving the most visible applications we see today.
That's the goal-driven agent. These are the optimizers, the problem solvers. They have complex reasoning capabilities to optimize a sequence of actions, specifically to achieve a defined, high-level objective.
So they're balancing multiple constraints: cost, time, efficiency.
To get the best possible result. They're perfect for that end-to-end workflow automation.
And it's that goal-driven agent that has to execute that 4-step workflow you mentioned flawlessly. Can you walk us through that circular process again? Because that feels like the mechanical heart of all this.
It is. The workflow is designed to be relentless and adaptive. It starts with perception. The agent doesn't just receive data. It gathers the necessary information from its environment.
So internal logs, external APIs, real-time sensor data,
Or vector databases that act as its long-term memory. It's pulling in everything it needs,
gathering the inputs, then deciding what to do with them.
which leads to reasoning. Here, the agent processes that perceive information, compares it against its goals and its policies, generates potential action plans, and then, selects the best course of action.
And that's where the LLM really shines.
Absolutely. That's where the nuanced decision-making happens, and then that decision transitions seamlessly into action.
Right.
This is the moment it interacts with the real world, sending an authenticated request through an API, updating a database, whatever it is. This is what separates it from a chatbot. It goes from talk to do.
And to close the loop, we go back to that most differentiating feature, the continuous improvement, the learning phase.
The learning phase is everything. The agent observes the result of its action. Did it succeed? Did it fail? Did it cause some unexpected friction? It uses that outcome to refine its internal models, update its knowledge base.
So it changes its future decisions.
It changes its future decision matrix in the reasoning step. So, for example, if an agent's attempt to book a resource fails because an API endpoint is slow or unreliable, the learning module updates its internal risk map for that API, so it will deprioritize that action next time.
That's a great example. And to manage all of that, especially with multiple agents working together, communication becomes critical. How do these things talk to each other and, well, to us?
Effective communication is structured into 3 critical flows. The first, and often the most technically complex, is agent to agent, A to A.
And that requires a shared context, right?
Yeah.
Shared protocols so they don't contradict each other.
Exactly. They have to share information, coordinate steps, resolve conflicts, all to achieve a larger goal without crashing. The second flow is human to agent. This is your interface. It's how you give it the high-level goals and provide feedback.
Which brings us to the third one, the agent's ability to talk to everything else.
That's the agent-to-environment flow. This is it engaging with external systems, APIs, physical infrastructure, everything it needs to actually execute its decisions.
Here's where it gets really interesting. So when we interact with these systems, we're not just, typing in keywords anymore. We're communicating intent, context, constraints. So how do we, the humans, effectively steer an entity that has autonomy?
The interaction has matured a lot. Users still rely on natural language, but the depth comes from the querying methods. It means mastering prompt engineering to clearly define the goal, the role, the constraints of the agent.
But it's more than just one good prompt.
Oh, yeah. More importantly, it requires multi-turn conversations and really robust context management.
Meaning the agent doesn't forget the 15 steps we just discussed. It maintains a state.
Precisely. The agent has to remember and prioritize past instructions, discussions, intermediate results. It mimics a true consultation. And critically, these systems move beyond text generation through action execution.
They use credentials, they connect through APIs, they talk to databases.
To implement their decisions,
Yeah.
sending that email, updating that inventory, spinning up those cloud resources.
Okay, but when you grant that capacity for real-world action, especially autonomous action, suddenly security, safety, and reliability become the most critical pieces of the architecture.
It's the definition of high-stakes automation.
So what are the essential guardrails? What do you need to build trust?
Trust is built on predictability and accountability, and our sources emphasize several non-negotiable guardrails. First, you have to clearly define agent roles and permissions.
The principle of least privilege.
Strictly, an agent dedicated to scheduling should never have permission to access sensitive financial data, period.
And what about malicious input? We know these models are still susceptible to manipulation.
Preventing prompt injection is paramount. Attackers try to bypass the agent's policies by injecting hidden or, adversarial commands into the query. You have to have advanced input validation and output filtering.
So you're screening the user's request and the agent's own action plan before it runs.
Before execution, absolutely. You need comprehensive guardrails and policies that are enforced by the system itself. And for high-stakes decisions, you must mandate humans in the loop for supervision or final approval.
So the human becomes more of a quality control point.
A critical one. And finally, you have to plan for the inevitable failure.
Right.
Robust planning for failure and recovery is essential. When an agent hits a new error, a broken API, a conflicting instruction, it needs a safe way to revert the state, pause, or roll back its actions to prevent a system collapse.
Building one secure agent is complex enough. But how do businesses scale this? How do you manage multi-agent collaboration on massive workloads?
Scaling demands structure and coordination. One key strategy is implementing detailed task documentation. The agents need to understand complex requirements without constantly asking a human. They need to read the internal manual.
And for that automated team,
Yeah.
that multi-agent collaboration, how do you manage conflicts and dependencies between them?
That requires sophisticated orchestration tools. These tools are like the system's air traffic control. They manage the sequence of operations, control the data flow between agents, and make sure they aren't stepping on each other's toes.
So the orchestrator would make sure the research agent finishes its work before the drafting agent starts writing.
Exactly. Which means all of this automation has to run without consuming infinite resources.
Good point.
Efficient resource management is non-negotiable. Agentic systems have to be designed to handle fluctuating workloads efficiently, dynamically allocating computational resources to prevent bottlenecks and control costs.
So this optimization and scaling is all tied to the tech stack.
Yeah.
What does the Agentic AI toolkit look like right now?
Well, if we connect this to the bigger picture, the whole ecosystem relies on combining several sophisticated technologies to enable that whole perception reasoning, action learning workflow. At the foundation, you have the agent frameworks.
Like LangChain and AutoGen, which our sources highlighted. Why are they so vital?
They provide the scaffolding, the modules, the structure. They're what you use to define those perception, reasoning, action, and learning components and link them together reliably. They are, in essence, the operating system for how an agent thinks.
So the framework builds the agent. What handles the connections to the outside world?
That falls to the orchestration tools, like NAN and Make.com. These are critical because they handle the workflow automation and, maybe most importantly, provide secure, pre-built connectors to external APIs and databases.
That's the action capability.
That enables the action capability. If the agent reasons that it needs to post an update to Slack, the orchestrator handles that secure communication.
And what about the system's memory? It's long-term memory.
That's where vector databases come in. They provide the agent's external memory, which is essential for that detailed context management we talked about. The agent can quickly retrieve highly relevant info from the vector DB to inform its reasoning.
Which all sounds like a powerful tech stack for solving really high-value business problems.
Yeah.
So what are the concrete applications we're seeing today where this value is actually being realized?
We're seeing major traction in areas that demand high efficiency and adaptive problem solving. Think of advanced personalized customer support,
Right.
where an agent can solve a complex multi-step issue like correcting a billing error that involves checking 3 different systems and issuing a refund all without needing a human escalation.
We are way beyond simple chatbots now.
Exactly. We also see huge gains in research assistance, where agents autonomously gather, cross-reference, and synthesize vast amounts of data to present targeted conclusions. And then there's workflow automation,
Handling things like HR onboarding, procurement, financial reporting.
end-to-end, which means businesses can achieve far more sophisticated data analysis faster. You can set up goal-driven agents to autonomously explore massive data sets and find insights without continuous human guidance.
And the overall goal is always the same.
It's universal, helping teams work faster and smarter by offloading complexity to reliable, autonomous systems.
So what does this all mean? We've taken a deep dive into the architecture of this agentic mind. The 4 pillars of perception, reasoning, action, and learning. We've defined the different agent types and established how that core workflow translates into real-world action.
And we've also stressed the absolute necessity of guardrails, clear permissions, prompt injection prevention, robust failure and recovery mechanisms to ensure these powerful autonomous systems operate safely, especially as they scale.
And this brings us back to a fascinating implication of those proactive agents and our reliance on humans in the loop. If a proactive agent is designed to anticipate future problems, to identify complex security vulnerabilities or potential failures that are 2 or 3 steps ahead, what happens when it flags a critical safety threat that the human supervisor hasn't even considered?
That is the turning point. It means the agent is now operating outside the known policy envelope. It forces the human supervisor into a complete role reversal.
They're no longer just checking pre-approved boxes.
No. They become a reactive analyst, suddenly tasked with understanding a novel, agent-identified crisis under extreme time pressure. It fundamentally flips the traditional management structure on its head.
An intriguing thought, especially as these systems become more capable of looking around corners than we are. Thank you for joining us on this deep dive into the architecture of autonomous intelligence. We encourage you, the learner, to continue exploring the incredible transformation intelligent systems are undergoing right now.